So we started nuclear by killing people. And I think we just never got over that.
Hello, everyone. This is the Space Cafe podcast, and I'm Marcus. So, nuclear is bad, right? I think we can agree. Oh, I don't know about you, but this is at least the way I was brought up. Nuclear energy is a tricky way to produce energy. And I'm a child of the 70s, and this is the way I was brought up. But there's a little twist. The decades have evolved, and we as a humanity, and this is why we do this podcast, are branching out into new territory. That is space. And space is not Earth. And as we know, space wants to kill us all the time. And one of the main reasons it's pretty dangerous out there is the radiation. So one could argue that space and nuclear are pretty much accustomed to one another because it's a radiating place. So in addition to some people who argue that if we want to set up shop for good in space, we can't do with solar energy. Solar energy is for visitors, they say, and if you want to stay for good, you need something else. And this something else could be nuclear energy. This is the argument or the discussion. And so I'm not taking sides. I'm just here to ask questions on your behalf, on my behalf, because, well, how are we going to do it? What is our energy source out there? And so I'm super happy to present to you one of the most prominent people in the field. Dr. Bhavya Lal is a former chief technologist at NASA, an MIT-trained nuclear engineer, and one of the architects of U.S. space nuclear policy. She worked at the highest levels of government to shape how we power our future beyond Earth. So this is going to be fascinating because, well, I'm trying to find out if this reshifts my attitude toward nuclear. And we'll find out. Before we do so, if you have anything you want to communicate in my direction, want to tell me, criticism, I'm highly interested in hearing your criticism, but also your love letters and whatnot. Please send them to podcast@SpaceWatch.Global. And now, my friends, without further ado, please welcome Dr. Bhavya Lal to the Space Cafe podcast. Let's go. Good. Whenever you're ready, Bhavya.
Okay, I'm just getting my glasses. I can't see. Okay. See, I thought that was the other thing. I thought this was audio. So I normally have my nuclear earrings on and I don't. So sorry about that. I had these very cool nuclear earrings. That's all good.
You got nuclear. So this is a fantastic conversation starter. What are nuclear earrings?
I have this amazing deep red set of earrings that is an atom, a model of an atom, the Rutherford atom model, not the quantum model. And it actually, if you count the number of electrons, it is a lithium model. I don't know why lithium. We need uranium-235 or we need plutonium-238, but I guess that's too many electrons to show on a laser cut piece of wood.
They are safe to wear. They're not radiating.
They are made of wood.
Bhavya, we just heard a couple of days ago that NASA considers to build a nuclear reactor on the moon. Good thing or a bad thing?
Oh, I think, Marcus, it's an excellent thing. And again, moon is just the start. The real prize is a scalable power backbone for the entire solar system. But let's start with the moon, right? That's where we are starting. The first thing to remind folks is that this isn't a new thing. Back in 2020, Space Policy Directive 6 in the United States actually told NASA to build and launch a reactor to land on the moon by 2027. That is, and then of course that was a policy directive. It never came with any money. So clearly NASA spent little bits, dribs and drabs of money, but obviously not enough. They made some progress, but obviously not enough. So the other really interesting thing happened, and these are important things to know, is in November of 2024, a few months ago, NASA actually put a stake in the ground. It said, it needs to have a nuclear reactor on Mars. And again, it didn't have a date and it didn't have a power level, but it did say that there is need for a power reactor on Mars. So, and obviously a lot of what NASA is doing on the moon is preparing for Mars, right? I mean, moon is a proving ground. So it makes sense to have a reactor, tested, et cetera, on the moon. So when we go to Mars, we are ready. So those are two important things to remind people that this didn't come out. I mean, for those of us who follow space, this didn't come out of the blue. It's a series of things that have gone on. And again, to your question, why is it a good idea? I mean, so night lasts 14 Earth days on the moon, and in those times and inside the polar craters, where we expect to mine ice, the sun never rises. Temperature plunges to minus 243 degrees Celsius. That's as close to absolute zero as you can kind of imagine. You can try solar and batteries, but you'd need football-sized arrays and shipping container-sized batteries, right? I mean, remember, the International Space Station generates about 100 kilowatts, and it is the size of an American football field. And then, of course, as I said, moon is just one place. The next place would be Mars, and Mars gets even less sun than the moon. Mars has dust storms, which can block sunlight for weeks. I mean, if you remember, the Opportunity rover basically died because it got too much dust and power ran out. And what nuclear does, it changes the equation. It gives you continuous high output electricity anywhere. Lunar craters, Mars in dust season. And again, it doesn't limit it to moon or Mars. Jupiter's icy moons, Europa. I mean, Europa has thick ice crusts, and we need to drill down to find, well, I hope life. So we cannot do any of that without nuclear. I mean, one of the things, so we just recently wrote a report on this. I hope you have a chance to connect to connect your users, your listeners, an audience with it. But we talk about solar lets you visit, nuclear lets you stay and build. So it isn't just about the moon. It's about unlocking Mars. It's about unlocking the outer planets and the rest of the solar system and beyond.
Can you refresh my memory? Matt Damon on Mars, did he rely on nuclear or was it solar powered? The movie The Martian.
He had an RTG, a radioisotope thermoelectric generator,
right.
Which he put wrapped in a blanket. And he used it to heat himself when he was in his little rover. Absolutely did.
Tell me, Bhavya, what is the big deal about nuclear in space? Because it seems like in public understanding, nuclear is bad. And this is why we do not do it in space. So what is the big deal about it?
So I think let me just talk about the vision here. Power is the currency of doing anything you do. So, I mean, I think maybe one way to think about it is, on Earth, we had candlelight, for millennia. And then one day, maybe in the 19th or 20th centuries, we got electricity and we got the electric grid. In a way, it is the same kind of big deal in space as it is on Earth to have what I call power abundance. So it used to be that we would design for constrained power. So the Voyager missions had about 470 watts of power. That's like a blow dryer for most of us. The New Horizons, the mission that went to Pluto, had about 200 watts. These are minuscule amounts of power. You can barely get anything done. In fact, to get the data back from New Horizons took 16 months because we just couldn't have those data rates. I mean, more importantly, it was a $700 million mission, and it took 9 years to get to Pluto, and it couldn't even go in orbit around Pluto, right? It was like, it whizzed past Pluto. It was almost like we put a camera on a bullet and sent it off. So I think that is the problem without nuclear. We just do not have, we have power scarcity, and having nuclear puts us in the world of power abundance. So now we no longer design to our power availability, we design to our needs, we design to capabilities. And I think that is the core reason we need to have nuclear. And to your point about, is nuclear bad? I mean, the space environment, and you observe that yourself, has incredible amounts of radiation, galactic cosmic radiation, solar radiation, and it's almost saying putting more radiation. First of all, unless something goes wrong, and we can return to that, you're not really even putting more radiation. But let's assume that something does go wrong. It's almost like you're standing in a hurricane and you pour a bottle of water on yourself. Like, do you really get wetter? There's just so much radiation in space already that adding this little bit of radiation doesn't mean anything. And in any case, these systems are so carefully designed that there is no danger or minimal danger of radiation or leaks.
Humans in space have been around now for a couple of decades, and still we have no nuclear powered or nuclear power plants in space. The ISS is not nuclear powered. So we do, as you mentioned, we do have a bunch of batteries, nuclear batteries, but no serious fusion reactors, the fission reactors, that is. So the question is, what is the problem here? Is this an ideological problem, or is it a security problem?
Yeah. So first of all, just a reminder that we did put a reactor in space in 1965. So, the United States has flown a reactor, and the Soviet Union has had more than 30 nuclear reactors in space. So it is already something that we have done for many, many decades. And I understand, China is working on nuclear reactors for space as well. But to your question as to what is the problem here, I think we've had some challenges, and the challenges aren't really technological. There's no physics problem here, right? The challenges are, we've never really had a mission pull up until NASA put its stake in the ground and said, we need nuclear power from Mars. So we didn't really need it. So we would develop, we would start, we would stop, and then nothing would happen. Another challenge we had was, so again, in 2000, we started a program at NASA called JIMO Prometheus, which was a 200 kilowatt nuclear electric propulsion mission to the moons of Jupiter. That was an overreach. So we didn't really know how to build even little things, and we decided to build a huge thing. And of course, before we knew it, it was too expensive and it was canceled. Another challenge we've had is there's no sort of central, there's no leadership. We do not have a place in the government which is a keeper of technology. Again, in the United States, there is, we have a nuclear navy, and which is one of the safest navies in the world. We've never had a single reactor, a single accident. There's an Office of Naval Reactors, which is part of the Department of Energy in the United States. And they make sure that we are always, at the technological cutting edge, as safe as can be, et cetera. There's no such thing for space nuclear systems. And last but not least, I would say there's a disconnect between timelines of development and decision timelines. So typically, in the United States, again, a lot of what I say is kind of with the U.S. perspective. Administrations are 4 to 8 years. So all decisions are made in these, 4-year timelines. Or in the Department of Defense, they have these, decision timelines that are about 5 years. But nuclear development timelines are 10 to 20 years. So these decision makers come, they are looking at their 4-year window or their 5-year window, and nuclear is 10 years, and they're like, okay, moving on. So they have just not taken nuclear seriously enough because it has never been ready. So those are sort of the 4 reasons why we haven't had nuclear systems. And of course, what we did in our report, which just came out a few weeks ago, we kind of tried to find a way to break out of this cycle of starts and stops and failures.
Will the next space station, once ISS gets decommissioned, be nuclear powered?
So I think this is a great question. And nuclear has a niche. You want to typically use nuclear when there's no sun, or when you need power density levels that cannot be provided by solar, or you are in a radiation environment such as the rings around Jupiter, where it is just too abrasive, too harsh, too corrosive. In Earth orbit, if there's plenty of sun, why would you use nuclear, right? You should be using solar. In places where you can use batteries, you should be using batteries. And you use nuclear when you need nuclear, when it enables some.
I guess it's a lot more expensive because, I mean, like, why should I use solar if I could use nuclear? Is it because of the price tag attached to it or something else?
I think in the near term, it is a price tag. We haven't developed nuclear systems, but at some point when we will have it and the costs are comparable, I think, and, we can make sure that, the safety levels are comparable as well. I think it would be neutral, but for the moment, nuclear is more expensive. So we just use it where we need it.
Let's just lay the ground for an understanding for me and for the listeners what kind of nuclear technologies we are even considering. So what forms can nuclear, or in what form can nuclear play a role in space? So I'm talking about propulsion, I'm talking about a source of energy, but there is a variety of energy sources. So could you lay the ground for us for all of this?
Yes. So the nuclear takes many forms. One of the forms is radioisotope thermoelectric generators or radioisotope heating units. These are essentially pellets of, it could be plutonium-238, it could also be other radioisotopes that decay. And the idea is that, this is natural decay of radioactivity of an element, and you just harness that energy. It could be alpha particles, beta particles, or gamma particle, although mostly it's alpha particles. And you can convert that into electricity. So those are RTGs. We've had them for 60 or more years. We had RTGs on all the Apollo missions. We have had RTGs on Voyager, Perseverance rover, the upcoming mission from NASA, I think Dragonfly going to Titan will have an RTG. So it's something, it's tried, tested, true. We know how they work. They're expensive, but we know, but we've had them for a long time. That's one. So, actually, those are two, right? Heating and electricity. The second one is nuclear power. Nuclear power in space is almost identical to nuclear power on Earth. We, fission uranium-235, produce heat, and that heat can be transported through a coolant. It could be on Earth, it is typically water, but it can also be other things. In space, we typically talk about things like, sodium and potassium, also, gas. And you convert that into electricity. So pretty similar. So those are the power options. Then we move into propulsion, where basically you have the same reactor and nuclear electric propulsion. And EP is basically you bolt on thrusters at the end of this nuclear power plant that we just talked about, and you can go anywhere in the solar system. NEP systems tend to have low thrust. But they have what's called very high specific impulse. So one could say very high gas mileage. So if you're thinking in terms of a Prius versus a Porsche, Prius can go a long distance with a small amount of propellant. So that's NEP. So Porsche is nuclear thermal propulsion, which is basically pretty similar to a chemical engine in a chemical rocket. You have a hydrogen and oxygen, for example, coming together in a combustion chamber, and it goes out the nozzle at very high speed, and it produces thrust. In NTP, you're basically separating out the heat source and the propellant. So then you can run a propellant over the heat source, which is a nuclear reactor, and the propellant can go at very high speeds out the back of the rocket, and there you get you get the thrust. And of course, because now you can choose any propellant you like, and the specific impulse is directly proportional to the molecular weight or inversely proportional. So then you use hydrogen because that is the lowest molecular weight gas. So that's the exciting advantage of NTP. And NTP gives you both high thrust and high specific impulse, although not as high as an EP. So that's why I use the Porsche versus Prius analogy, because Porsche takes a lot of gas, But it goes 0 to 60 in 3 seconds or whatever. I don't know the number. Sorry, I'm not a car aficionado. So those are, and then of course now you can. There's things called bimodal systems which combine an EP and NTP in the same system, and I'm sure there's other exciting alternatives as well. Some people have talked about instead of having a solid core of uranium that fissions, you can have it's so hot that it's liquid and gaseous. So then you can start to get into really 50, 100 years out, and we can talk about that another time.
Would just because you mentioned the Voyager probes, would they still be active as they are currently if they weren't powered with nuclear batteries over that vast distance of time? Is there any other form they could be powered with?
I mean, nothing that we have. I mean, in principle, you can power it with matter, antimatter drives. And, we all watch Star Trek and there's warp drive. And, so there's
Maybe
a lot of imaginary things. But in reality, fission is the only thing that we have. And as you go deeper into the solar system, there is no solar flux. So not only could we not, and again, it also gets colder because as you get farther away from the sun, you have it's colder and colder, and the electronics will stop working. So both from the point of view of collecting the data, right, you need to power the instruments, which we won't be able to do without RTGs, but also we want to send the data back. So even if the Voyager missions kept on going in the solar system, and even if they maybe collect some information, although it's highly unlikely, they're not going to be able to send it back. So yes. And again, these RTGs are, they have a limited life. I mean, they are decaying, right? So at some point, the radioactivity levels would be so low that they cannot generate any more heat, and then we will stop. And so then Voyager is dead. But for now, I think it's well over 20 billion kilometers away. It is outside the solar system, and it was only made possible because there was an RTG on board.
Speaking of solar, I'm imagining that solar has its limits the further away from a star you're traveling. So I guess solar makes sense if you're in the vicinity, like Earth to the sun. But the further you go away, is there a place where you would say it doesn't make sense? And I guess it's most of the places in the universe, because most of the places in the universe are too far from stars, and that solar makes any sense.
Right. So, I mean, solar flux reduces, 1 over r squared. So, there's obviously enough on Earth. I think we get, maybe 1 kilowatt per square meter. Somebody should check the numbers. At Mars, it's reduced by a factor of 1 over 1.5 squared because, it's 1.5 times farther away, or it's 1 over 2.25 compared to Earth. And if you keep going down, and by Jupiter, there's hardly any solar flux left. And then, Saturn, Uranus, Neptune, Pluto, there isn't any sun. And in principle, you could be in the vicinity of another star, and then suddenly you can use that star's energy. But for the moment, for the next 100 years or so, while we are still kind of stuck to our solar system, we only have the sun as our source of energy, and it is either that or nuclear. I mean, obviously we have batteries, but batteries don't last very long. The example I have is, there was I'm sure you know about this, the Huygens mission, which was,
yes. Yeah.
Again, a cost of about $600-700 million. It had no more than 3 hours of battery life, most of which was planned to be used during the descent to the surface. Planners expected to get at most 30 minutes of data from the surface. And again, hundreds of millions of dollars for 30 minutes of data. And again, another European mission, the Philae lander, cost about $250 million. It went into hibernation after just 60 hours of operating, after landing on the comet 67P CG, and it did not operate again. So, so we spend a lot of money on our space missions, and we want to, as taxpayers, we should want to get more out of all the effort that our scientists and engineers put into designing these missions.
more mileage out of our investments. So, but again, this raises, and so I keep coming back to the original question: why, if someone is investing hundreds of millions of euros/dollars into something, and then you have a battery that lasts 3 hours, I guess the valid question could be: is no one thinking about alternatives, which of course I'm not assuming, or are legal and policy in place that do not allow for such considerations?
I mean, but tons of people are thinking about it. In fact, this announcement from NASA is exactly because people think, and again, it might seem that it came out of left field, but we have been investing in nuclear for a very long time. In fact, some of the studies that have been done show we've spent in the United States alone, more than $20 billion developing these systems, right? So we understand they're important. We have been investing in them, but I think what we haven't had until recently is a very strong mission pull. And I think the NASA announcement gives us that strong mission pull. Let me give you an example of a strong mission pull. So, I said at the start of our discussion why the Soviets launched reactors. Why didn't the rest of the world? Well, they needed to follow the American fleet all over the world. They did not have radar systems that were very good from high altitudes. They needed to operate at low altitudes, but then at low altitudes, there was a lot of drag. So they couldn't, they needed something to keep the satellites in orbit. They didn't have good solar panels. So they had no choice but to use nuclear systems, right? So that's why Soviets launched more than 30 reactors in the 70s and 80s. And that is a really good example of nuclear being enhancing, as in making something that we were going to do we could do with other means, but it's just a little bit better, versus enabling, where if you didn't have nuclear, you couldn't do it at all. And I think nuclear makes a best case when it is in that latter scenario. So on the moon, as I said, there's 14 days of day, right? You do not need nuclear for that. You need nuclear for the 14 days of night, where the temperature plunges to near zero, and the United States and its allies are planning to be on the moon for an extended period. They will have humans. There's private companies that want to mine things on the moon.
All this means that if we're taking some of the visionaries we have on Earth seriously, the visionaries selling us a dream that in the next 5 to 10 years there will be humans on Mars. If ever that is possible, that's the vision. But still, if we want to do something or achieve something like this, we need also to develop those nuclear solutions right now. So that means if those visions are being taken seriously, someone is developing those technologies right now on Earth. Is that right?
That is correct. NASA has been working on fission surface power for the last 5 years, and they have made a lot of progress. There have been space nuclear programs in other parts of the government as well. And again, I don't know enough about what's happening in Europe, but the Department of Defense is developing nuclear power systems. There was a program that was recently ended at DARPA, an agency within DoD and Department of Defense that was collaborating with NASA to develop nuclear thermal propulsion. So there have been efforts. It's just unfortunate that they have ended. And again, to repeat myself, I think one reason they have ended is because there hasn't been that mission pull for something enabling up until now. And again, there's a whole bunch of factors that have come together. So mission pull is just one. Another one is we actually now have policy clarity. In 2020, the United States came out with what's called National Security Presidential Memorandum 20, NSPM 20, that laid out the process for how you would launch a space nuclear system. Up until 2020, there was a process. It was called PDNSE 25, just acronyms and numbers, but it wasn't clear enough. And with NSPM 20, now it's clear. So that actually even allowed commercial companies to start to develop nuclear systems. And many new commercial companies actually came about because now there's a pathway to launch. Other things that kind of have happened is, it used to be that we could only use highly enriched uranium to develop, to launch or operate nuclear systems in space. In recent years, some researchers determined that you can actually use low enriched uranium, or what's called high assay low enriched uranium, HALEU. And that was a huge step forward, because now suddenly you weren't using weapons grade uranium to launch. And again, there's some security concerns around using weapons grade uranium. So that's another really big, important step. Another one is private sector readiness. So on the supply side, there is a growing commercial terrestrial nuclear industry. These are companies that are investing. There's venture funding. They are looking at very exciting new designs that actually have space applications. So in the olden days, we only had water, pressurized or boiling water, PWRs or BWRs, pressurized water reactors or boiling water reactors. Some of these new reactors are using technologies that are actually relevant for space. So, for example, sodium-cooled or helium-cooled reactors. And the last big development is on the demand side as well. So, there are some private companies that want power on the moon, and so they're willing to invest in that. So, a lot of things have come together that suddenly now we have, the sign that maybe this is the time where we can actually make things happen. I'm an optimist.
I assume that firing up a nuclear reactor on Earth versus activating one in space is not equally difficult / easy. So it's not the same, I guess. So where are the main differences between activating a reactor in space and on Earth?
So one major difference already is that right now, at least, we are looking at space reactors that are in the tens to hundreds of kilowatts. And just to give you a sense, 100 kilowatt is basically a commercial air conditioning system. So it is not a very large reactor. And actually, I did an analogy in my head. If we do a 100 kilowatt reactor on the moon, which is what NASA has announced, it is basically about 15-ish metric tons, so it's the size of a large African elephant. And it's going to need a very large radiator, and we can talk about why. And the radiator is the size of a basketball court. So, those things look really big, but compared to the 1,000 megawatt reactors, which are huge pieces of land on Earth, they are quite small compared to Earth reactors. The other really big difference likely is going to be space reactors will be very highly autonomous. We are not going to be having, humans power them up and down. And again, though that is, one of the challenges we need to address. We need to make sure we know how to manage a reactor completely autonomously.
I assume that the highly enriched uranium needs to be fabricated, needs to be produced on Earth. So, or is there a way to in situ produce highly enriched uranium wherever you are, on Mars or on the moon?
Right. So one thing, as I was saying, that we are actually moving away from using HU, highly enriched uranium. We are going to be using low enriched uranium, which we already produce a lot of on Earth for Earth uses, and some of the newer companies, like I mentioned, will be using this new kind of low enriched uranium called HALEU, high assay low enriched uranium. And yes, that we are not, at least not in the near term, we are not planning to be mining uranium on other celestial bodies. It will be, these reactors would be fueled on Earth, and they would be sort of one-time fuel. There's no refueling, at least not in the way we are currently planning our space nuclear reactors.
Do we already know that there's uranium sources off Earth? Do we already know about them?
Off-Earth geology is in my area, so I don't know. But I wouldn't be surprised if we find all sorts of elements. The solar system is big, And we have a very large, asteroid belt in between Mars and Jupiter. So I wouldn't be surprised, but I don't know. In any case, it is probably going to be very difficult to mine. And remember, mining is just one piece. After you mine, you have to, refine, you have to enrich. I mean, there's a lot of steps before you yellow cake, which is what it's called on Earth. To go from yellow cake to a fully manufactured fuel rod is a lot of work. I don't think that unless I don't know if you watched this TV show Expanse, where all these miners
yes,
live.
Absolutely. Yeah.
So I don't think
Loved
we are
it.
there yet.
What is the legal framework right now on Earth regarding nuclear in space? Is there any restrictions? Do we have a global understanding of what we can do, what we cannot do?
So as I said, we have been launching nuclear systems, for the last 60 or so years. So I don't think that there is, anything crazy new that we need to be doing. There is, the Outer Space Treaty, which is, one of the biggest treaty that guides our activities in space, has no restrictions on the use of nuclear. The only thing it restricts is, weapons of mass destruction. So, let's not be making bombs in space. And, obviously nobody wants to do that. There's also a policy that I think is called Principles 4768 or something like that, that has a regime for safe operations. And again, these were developed by, smart people who know nuclear well. So they are very aligned with how we are thinking about launching nuclear systems. So there are no deal breakers. There are no showstoppers. And that's internationally. And of course, at the domestic level in the United States, there is enough both congressional policy and executive branch policy that lays out how you would do this. There is nothing that stops us from doing things in space. I mean, one thought that does come to mind is the Outer Space Treaty Article 6 says that every private sector activity must have authorization and continuing supervision. So if the reactor that operates on the moon is private, which is what it seems, again, I don't have good insight into what NASA is planning, but let's assume that they're expecting private parties to launch these reactors and give them and basically sell power to NASA and others on the moon. There isn't any way to provide that Article 6 coverage, the authorization and continuing supervision beyond some minimal things. So I think we probably need to work through that. But there's a lot of work underway on that. In fact, I understand that there may be some executive order in the United States coming out that gives the U.S. Department of Commerce that authority. So I think we are working towards a solution on that.
Mm-hmm. A very practical question I'd like to discuss. So I could imagine that once we're ready to launch something nuclear into space, nuclear other than a battery, but something more nuclear into space, what is the actual risk when launching nuclear materials into orbit toward Moon or Mars, and how is it mitigated? Of course, I'm also talking about containment systems. Are there any interesting solutions already, or is this still a problem and needs to be developed?
Yeah, so a lot of the risk depends on the actual design of the system. But one thing that is important to note is that any reactor that is launched, or at least any reactor that's launched from the United States, will be launched cold. And by that, what I mean by that is they will not have any fission. They would not have been used up before, so there's no fission products. And fission products is essentially what is radioactive in a nuclear reactor. Until you start a nuclear reactor, it's just like any other element. So uranium-235 is not chemically or radiologically that much more toxic. In fact, the James Webb Space Telescope, which was launched in 2021, I think, had a lot of beryllium, and beryllium is actually poisonous. Almost every launch that we have of rockets in space have some amount of hydrazine, which is a chemical. It's a propellant, and it's highly toxic. So we have already policies in place about launch of toxic materials, but uranium-235 isn't toxic in the same way. So that's one thing. The reactors would be launched cold, and they will not be turned on until they reach a place which is deemed safe. So it might be thousands of kilometers over Earth, or it might be some part of the moon, which is decided that this is where we will put the reactor, and this is how we will make sure that it has a good safety zone around it. The one thing that some people have talked about is what happens if there's an accident and the reactor falls in ocean water, and it falls in this very specific configuration and angle and compression that it goes what's called critical in the nuclear lingo. Those are the things. That would be one scenario we would avoid to design. So, and then again, there's a lot of designs people talk about. For example, you could break it up into two so that two halves never come in contact. So that's a design problem. And again, there's in the regulations in the United States and Europe are sufficiently stringent that a lot of these issues will be addressed before reactors launch. There's a process called NEPA. There's an environmental review, and then there's another process called, and again, I'm not going to be able to remember what it stands for, INSERP, and it's a review board that looks at safety. There's a thing called SAR, Safety Analysis Review, which is prepared by the team designing the reactor that says, hey, this is what they did to make the reactor safe. And then an outside body does what is called a SER, S-E-R, which is a safety evaluation review, but they basically evaluate the SAR. So there's many layers of review before a reactor has sign-off. And based on nuclear safety, National Security Presidential Memorandum 20, NSPM 20, a fission reactor will likely need sign-off from the President of the United States. So a lot of review is going to happen before a reactor is launched.
Is the bad reputation that nuclear has on Earth, is this an exaggerated reaction to perhaps a historically grown understanding of nuclear technology? Of course, I'm also talking about the Cold War period and whatnot. So what is it with the perception problem that we have with nuclear?
That's a great question, Marcus. And again, I'm not a historian, but if I had to guess, the start of the nuclear age was with an atomic bomb. So we started nuclear by killing people. And I think we just never got over that. I think if we had started nuclear as for peaceful applications, we probably wouldn't worry as much, because even if you look at the actual accidents, Fukushima in Japan, people who died were the people being evacuated from the city, not from radiation. 3 Mile Island, considered the worst accident in the United States, not a single person died. So it is truly perceptions about what might happen, but in reality, this is not how it has been. And part of, I think, for those of us who think about this, part of our job is to actually, not underestimate the safety issues and how citizens think about nuclear and try to educate. So, for example, standing outside a nuclear reactor on Earth is for a whole year. Like if you just don't go anywhere, get a chair, sit outside a nuclear reactor for a year, that's as much radiation as you would get in a chest X-ray, right? So I think we just need to talk more about it. We need to explain, and hopefully, we can help our, fellow citizens understand the pros and cons.
I'm being very open with you. I'm a child of the 70s. I was raised also anti-nuclear. This is how I grew up. And so I'm just wondering, because this is a question that's rarely discussed, or I'm missing that debate, in how far does nuclear technology also undergo an evolution as a technology? Does it, like the nuclear reactors we have on Earth, they are from a certain period when they were developed. and so they are decades old. So are they getting safer? We're hearing that in China there is newer versions, the sodium cooled reactors and whatnot. So is this technology getting safer?
I think so. I am not completely current on Earth technology. I would say we are working harder for the reactors to be what's called being passively safe, as in safe without actively fiddling with knobs and things. So I think that's what happened with 3 Mile Island. In order to make things better, they switched off some things that made things worse, right? So I think the big lesson from those times was, can we do something that if something goes wrong, we just go, oh, don't touch anything, and it'll come back. It'll shut down by itself. So that's part of what I think some of the newer designs are, and we are trying to make them safer by making them passively safe. So that's one thing I know we are doing. But I don't think the old reactors are less safe at all, in that while they may need to be actively managed, that active management does happen. And, most of the reactors in the United States in particular, I know more about, they're actually extending their lives because they're just working so well. So I don't think there's any reason to think that older reactors are not safer.
Where's the big hurdle now? We're in the middle of a space race. This is a huge industry that is getting ever more momentum as we speak. And there are grand visions on the horizon as to what we can do in our vicinity, on the moon, on Mars, etc. Do you think that nuclear will play a role in the years to come, or is this still a niche technology that needs to find its place?
I think the debates are more around how do we make it happen, not that if it needs to happen. I think we are, going to Moon and Mars is something that the United States at least has decided to do together with allies in Europe and Japan and India and other countries. And as we go deeper into the solar system, as we try to do more things, we will need high density power. I mean, it's the same argument I made at the start of our discussion. If we had only candlelight as opposed to electricity, think of how little we could do. It is essentially the same idea in space. And as we want to do more things in space, we've kind of, done the little stuff, right? We've been to every planet in the solar system. Now we want to orbit every planet, right? Now we want to land on Europa. We want to dig through the ice. And the more of these things we need to do, the more we need a source of power that is, higher density, doesn't need the sun, can be taken more easily. And the other big breakthrough we've had is, or we will likely have, is that we will have heavier lift. So we can actually now take bigger things as compared with before, where everything had to be super extra duper light. So we were trying to make the lightest solar panels we could make, etc. So now we can take heavier things, and nuclear reactors will likely be heavier than some of the other things. So so I think a lot of stuff is changing that we will have no choice. And again, even nuclear technology is evolving and getting better. So I'm very optimistic and enthusiastic.
Love that. That's rarely heard that someone is enthusiastic about nuclear. So, but it's your job, obviously. So I'm very thankful for your wisdom and expertise. You just mentioned Europa and digging through the ice shield of Europa. I think this topic is so fascinating. We just should talk a little bit about it, what that means. So Europa has a huge ice shield and potentially an even huger ocean underneath it. And we're interested in tapping into that unknown body of water. And this would be handled through a nuclear-powered drill. Could you explain what that means?
Well, first of all, I don't think I don't think there's a mission where this is being done. I'm not a space scientist, and I hope you will invite, a space scientist and talk more about this. The idea is that we need to dig through the miles of ice, and again, there's no sun. So, once you dig, it freezes on top. So you need to somehow keep it liquid. So nuclear is obviously an obvious option, but maybe there's others too. And again, even with a nuclear, you could have a radioisotope, which is just, basically a hot rock, and the hot rock just sinks, versus a fission where you're, actively breaking up atoms. And again, I don't think those decisions have been made. I'm just positing that, as you do hard things, you will need more power, and nuclear is a way to do more power. But I am not aware of how scientists plan to go dig through Europa. There's actually a really awesome movie called the Europa Report, which everybody needs to watch. In which
the Europa Report?
Yes, it is. It is just a fantastic, fantastic movie, and it's basically the story of we discovered life on. We believe we've discovered life on Europa, and they send a human mission to Europa and how they find life, and it was just amazing, amazing movie.
Do you think there's life out there somewhere?
Absolutely, I know it.
Well, absolutely. This is kind of very spontaneous. So you have to tell me more about that. Why absolutely? Is this a gut feeling, or is it a feeling from a scientist doing the statistics?
Fair point. It is more of a wish than than really knowing for sure. I think, was it Carl Sagan who said something like, if there isn't anybody out there, that would be a damn, shame, waste of space or something. And we have there's billions of stars. Each of the stars has planets around it, and again, the Drake equation. And if you kind of do the math, it just is reasonable that there is life. But then on the other hand, there's also the Fermi paradox. Like, if there is life, where are they? And there are all these, people have all these ideas. So a few months ago, I was visiting the SETI Institute in San Francisco, and had a chance to talk to a lot of the scientists there who had all sorts of really interesting theories on why we haven't found intelligent life. I'm actually very, very certain that there is microscopic life even in the solar system. What I'm more concerned about is if there's intelligent life. And there's this theory of the great filter that does life at some point extinguish itself? And at what stage of the great filter humanity is at, right? Will we extinguish ourselves before we become spacefaring? And has that happened? So that is a question that I do think about a lot. That is there intelligent life out there? Because that is of way more interest to me. I mean, I think it's great. I mean, I think we'll find life in the solar system in this decade. I'm sure of it. But that's microscopic life, whether it's on Enceladus or Europa or even Mars, right? I mean, it's important, obviously. But what's exciting is if there's Star Trek life.
I like this great filter theory. I've come across it a while ago, and I think we are, as a species right now, we are trying very hard to not make it through that filter at the moment on Earth, because we're doing everything to extinguish ourselves. So maybe this is a good moment to reconsider, because if we want to find life out there, and if we find life out there, that means that another civilization or another species was smart enough to make it through that filter. And so this should give us hope that we have a future, and there is a future beyond the mindless craziness that is going on our planet right now.
I 100% agree with you, Marcus. In fact, if we find microscopic life, that is actually cause for some sadness, because it kind of gives you more data that that more life has gone extinct than not. Maybe my optimism is trying to look past what you just said. It seems that our efforts to extinguish ourselves. And actually, that's why working on space gives me great hope. I mean, most of my friends and colleagues who work in space are just optimists. They look, they imagine a better future than the present. And, all of us try to make us go past all of the craziness of what we see around ourselves today.
This is my personal view on things. I think what we're experiencing right now is the last breath of an old system struggling to survive, and knowing at the same time that the 20th century, the patriarchal, white, old men-driven system is over. And I think this is what we're experiencing right now. We have still white old men trying to keep that 20th century mindset alive. But we all know it's over. We're in the 21st century. And I'm very positive that we're going to make it through it.
Yeah, I'll stick to my knitting and stay an engineer. But yes, I mean, obviously, I always think the future is brighter than the past, and we need to do everything we can to make sure that that is the case. I think the best way to predict the future is to make it, which is kind of what I'm trying to focus on.
Yeah. Bhavya, I have a nerd question for you, because if we're talking about civilizations out there, we would need to take a look for ourselves, and so we would need to travel very far. And there's science fiction movies and books, and based, of course, on scientific theory. And there's one theory that you use nuclear bombs as propulsion method. So you throw in a certain period, throw nuclear bombs behind your spacecraft, and you detonate them and use this as a propulsion system. Is this something beyond science fiction? Does this make sense?
So you bring such a great historical point here. And just for those of you who don't know this, there was a program called Project Orion in the United States in the 1950s. Started in, I think, at end of the 50s, ended in mid-60s. And the fundamental idea there was to use a series of controlled nuclear explosions, basically detonating nuclear bombs behind the spacecraft to generate thrust via a pusher plate, effectively turning nuclear blasts into the engine of interplanetary travel. And they had really ambitious mission dates. This is, they said Mars by 1965, Saturn by 1970. So they were talking about with people, right? It was an extraordinary concept. I mean, imagine a Saturn V, the Apollo rocket carrying hundreds of nuclear bombs as pulse units to propel it. But the program was canceled because there was a test ban treaty that was signed by the United States and the Soviet Union in 1963. And then obviously there were concerns about environmental safety and nuclear proliferation as well. I
completely do not understand where that comes from.
I think for people like Freeman Dyson, who was a famous physicist of the time, I think they thought it was too far on. You both do high ISP, high efficiency space travel, and get rid of the nuclear bombs. This was a time when there was a lot of creativity, and people thought they could do anything. And obviously, over time, we learned that there's some things we just shouldn't do. And I don't think we are going to be detonating nuclear bombs to get into space
anytime soon.
No.
Bhavya, if the call came, would you be ready to go into space? How far would you travel?
I would absolutely say yes, but I would want to beg my husband and daughter to go with me. I don't think I'll be happy without them. I can't imagine the thought of, leaving them behind. So hopefully they'll come with me and then I will go. How about you? Would you go?
I think I would go. I would maybe need to have a discussion with my family. I don't know about my teenage daughters. I don't know if they would come or maybe prefer staying with their friends. But anyways, yes, I think I would go. But my question to you has a reason, because we have a fun tradition here on the Space Cafe podcast. I'm asking my guests this question because usually traveling in space is in the beginning an exciting thing, but I could imagine it wears off pretty quickly and gets boring at some point because those travel times and distances are long and vast. So my question to you is, to keep your spirits entertained and to keep yourself from going insane, what's the one piece of music you would want to bring on your playlist on that interstellar or interplanetary journey?
Oh, goodness. I would probably take music from the 1970s. I would take ABBA with me. Dancing Queen. How about that?
Fantastic. We haven't had this before. Fantastic. I love that tune. So, by the way, I'm going to put it up on a real playlist on Spotify. It's the playlist for the aspiring space traveler. And Dancing Queen will be added to it once this episode goes online. So thank you so much for that contribution. And my last question to you, Bhavya, I challenge you to share with the audience a strong shot of inspiration, sort of an espresso for the mind. And you pick whatever kind of topic you want to pick. What's your shot of inspiration you'd like to share?
Think of abundance. We have spent our entire lives, and the entirety of human existence has been about scarcity. And we are heading into a time where, whether it's power or it's other resources, as the solar system opens up, we have access to resources and we have more abundance. We bring the solar system into our socioeconomic realm and we grow as humanity. That's my shot of inspiration. We are entering an era of abundance.
And we are most likely, we will live to experience and see all this firsthand. Isn't this an amazing moment in time in human history?
Absolutely. We are at a very special time in human history, and I cannot be more excited about what's coming next in our lifetimes.
If we make it through that filter.
If we make it through that filter, which we will, because we are working towards it. Many of us are working towards it, including you.
Thank you. Thank you, Dr. Bhavya Lal, for taking the time. This was a lot of fun. Thank you so much.
I super enjoyed it. Thank you again, Marcus, for your time too.
And that's a wrap, my friends. I don't know about you. It did kind of shift my attitude toward nuclear. Not on Earth. I'm still against nuclear on Earth, but I think it's a no-brainer for space. Why am I against it on Earth? Maybe because my lack of knowledge is hindering any other thoughts. Lack of knowledge regarding new forms of nuclear reactor technology. Because honestly, the ones we're criticizing, the ones where all that, in my head, anti-nuclear attitude and sentiment comes from is old generations of nuclear reactors. I do not know about the new versions. If there are new versions, I hear that China does some interesting stuff and whatnot. So I don't know if those things are any safer. And just to be on the safe side, let's go for nuclear if need be and if it must be in space first. Maybe that's a safer way to put it. I would love to hear your position on all this. Drop me a note at podcast@SpaceWatch.Global, or let's fire up a conversation on LinkedIn at my profile. If this is of any use to you, this episode, consider sending it or sharing it with a friend or someone who may take a benefit from this discussion. And without further ado, there's nothing more to say other than thank you from the bottom of my heart that you're still listening to all this. It's really a lot of fun to do this and a lot of fun to see the little SpaceWatch.Global universe grow. So thank you. I would like to reach out to you personally, but it's a little tricky. But thank you. I'd like to address you by name. So put in your name now. Thank you, my friend. Bye-bye. Until in 2 weeks from now.